Okay, so first I pass around a memory stick with the video recording from yesterday, the PDF notes that I made, and also one exercise that's what we are going to work with today. Okay. Um, the notes are also on my website, but I don't have good internet connection to upload the video. The video is quite big, okay, it's like 600 megas. So I will do it once I'm back in Norway. But in the meantime, you can copy from the memory stick. Remember not to cut it, otherwise, the other ones won't be able to copy. Okay, so we are, just to go back to what we were doing, okay, we are trying to, we came to the conclusion that the rate versus time is very important to calculate. First, due to contract purposes, and then for calculation of revenue, okay, and calculation of cost. So this is a critical component that we have to find out how the field is going to perform. Okay? And to find out how the field is going to perform intuitively, we gave a mechanical analog, just that you understand in your head how it behaves. But actually, when we are doing calculations, we have to use a more sophisticated method. Okay? And for that, we introduce the concept of flow equilibrium. Flow equilibrium, we can use it to describe complex part of a production system. Okay? So even though it sounds like a trivial or very simple concept, you can use it to model very complicated systems. So yeah. So we said we make two curves, we define a point in the system, any point. We know we have some preferred points depending what we want to do. If it's choke management, if it's artificial lift, we select different points. But the basis is I have always two boundaries with fixed pressure, okay, at a given point in time. Remember, that pressure is going to change with time, reservoir pressure. But at any given point in time, it's constant. Doesn't matter how much I produce, it's going to be constant. It's only after some time has passed that is going to go down. So I go from that point, co-current, I reduce the pressure due to the pressure drop. Here I have in the formation, and then I have in the tubing until I reach the point of equilibrium. Okay. And then I go from the other boundary, which is usually the separator, that maybe I want to make a short comment today. And you go counter current, that means that you add up pressure until you reach that point. Okay. And then the two, if you put those two together, the only way that they can operate is at the intersection. That's when the pressure is the same. Okay, unless you have some equipment in between. Okay, and in that case you can achieve rates to the right if the equipment is giving energy, or you can operate on rates to the left if the equipment is taking energy from the system. Okay, but always think in these terms: energy available and energy required. Okay, and is going to operate always at the intersection unless you put another equipment that will bridge the difference. Yeah, so then we enter about the concept of IPR, and that's something very useful. Okay, we know that there will be a transient in the formation. Okay, but that transient happens so fast that really we can neglect this transient effect. It's very interesting for other things. Reservoir engineers like to get the transient to know the size, the volumes, the permeability, all kind of things. Okay, they are focused on the transient. For us, we just interested that's very short. Okay, it happens in a matter of hours, and after you reach the boundary, you can use an approximation. You can just say, well, my equation now will be simply a function of reservoir pressure. Okay, I don't have time at all in this equation. Of course, when I go in depletion, this reservoir pressure will change, will start to drop. So that's where the time comes in, but I don't have time anywhere in this equation. If I were looking at the transient period, I want to know exactly what happens here. I have to take time into account. Okay? And for most cases, only some very tight formations when you're talking about nanodarcies or zero point zero 0.01 millidarcies, then it becomes relevant. Then you have to use something else. This approach doesn't work. Okay. We said for gas, and we are, even though we talk a bit about oil, we are focusing this course mainly on gas because that's what you have in Tanzania, and that's the main business. So for gas, we have this simple equation that came from first empirical measurements in the field. People saw that it had that behavior, but after it was verified by theoretical derivation. Okay, that we don't have time to make it here, but you can take Darcy equation, Darcy law, and then you can assume radial geometry, and then you can integrate the equation, and it will give you a similar function. Okay. Then we say, well, we have oil, etc. Then we have the tubing equation. Okay, well, again for dry gas. Good morning. Okay, and it looks something like that. Okay, remember, DCT and DS, they are made with an average deviation factor. Okay, that means in principle, we need to have the pressure, average pressure, and average temperature. Okay, but in the real case, we say it's not so much, the variation is not so significant to give you a big change in CT. Okay, so we were looking at equilibrium we made at the bottom hole. It looks something like that when one curve is IPR, one curve is TPR. Okay, now let's see. So let's just refresh that part, not making any calculation, but just making it schematically. Okay, we have our well. Okay, we have here some PR, PWF, and P wellhead. Okay, and here very close we have our separator. Okay, very, very close. And I'm making flow equilibrium at flow equilibrium, we say downhole. Yeah, at the bottom of the well. So let's see, here we have Q gas. Remember, we always use the standard condition rate. Okay, always. And that, if you ask, if you ask a chemical engineer, he will tell you, the amount of kilomole per second. If you ask a mechanical engineer, he will give you mass flow, kilogram per second. But if you ask a petroleum engineer, that's what we use. Okay, standard condition rate. Complaining the computer. Okay, so we make PWF. We know one of them looks like that. Okay, the available pressure, that will be IPR. Okay, and then the other one looks something like that. Okay, the TPR. Okay, now let's see something else. So how let's say here, variation of, let's say, tubing size. Okay, of tubing diameter. Okay, what do you think will happen with the intersection if I change the tubing size? Let's say I make it bigger. Okay, I make it the diameter, I make it just bigger. What do you think it will happen with this curve? First of all, which curve is going to be affected? The TPR, right? That's the one that has the tubing inside. Okay, now what do you think will happen? Am I going to get more rate or less rate if I make a bigger pipe? More rate, right? And another question, at no flow, is the point the hydrostatic pressure going to change? If I have, let's say, have no flow, right? And I have this case, P1, P2, or I have this case, I have a big pipe, and then I have P1, P2. No flow, just simply a hydrostatic column. Is the pressure going to be different? No, right? Okay, you have exactly the same. It doesn't matter if you have a pipe of 1 meter or if you have a pipe of 1 millimeter. Okay, you're going to have exactly the same hydrostatic change. Therefore, this point in the origin, when you have no rate, it will be the same for both curves. But for a bigger diameter, one of them will do something like that. Okay, so that will be, let's say, diameter phi, that's phi1, which is greater than phi. Okay, and if I use a smaller diameter, I go on the other side. Okay, so I go like that, phi2. Okay, where phi2 is less than phi. And that tells you how the diameter of the tubing affects your equilibrium point. So just to make just to take a small detour, how petroleum engineers define this diameter, okay? There are a few considerations. First, you want to minimize, okay? So let's say here how to choose the diameter. And that's something that we have to do in the field development process, okay? So how to choose the diameter of the tubing, okay? One of the things we have to take into account is to minimize tubing delta P. Okay? Why? Because this one will give me a maximum rate. Okay? However, we always have to make sure that the increase in diameter is like it gives me a significant increase in rate. Okay? Because what happens if, let me make it bigger. Okay, again I'm plotting, making the same plot, but now I have the TPR looks exactly different. Looks something like this, and for one diameter, and if I increase the diameter, it gives me something like this. Okay, you see that the difference in rate is not really very much, okay, because the TPR is relatively flat. Okay, that means increasing the diameter, let's say that this one is, I don't know, 4.5 inch and this one is I don't know, 7 inch. Okay, doesn't make any big change in the rate. So this pipe of bigger size is more expensive, it's more difficult to install, you have a lot of other considerations. Therefore, it's not worth it. You can just use the 4.5 inch diameter and that will give you still a good rate. Okay, maximize rate, and there is another consideration. So minimize tubing cost. Okay, so we always have to look how the TPR is, and if by increasing the diameter we're going to get a significant increase in rate. Okay, there are also other things we have to take into account. One of them is erosion. Okay, we have to avoid erosion. If we make the pipe too small, the velocities. So let's ask, let's say maybe, okay, let's say we have our tubing, right? And we have certain rate flowing through the tubing, okay? So I'm going to ask you now, what is, if we plot here Z versus, let's say, the local rate, okay? Here I'm not talking standard conditions rate, it's just the local rate, okay, of the gas. How is it going to go with depth, okay, when I go up? Okay, we say, right, let's say here, right, we have M1 mass flow. So first of all, the mass flow through the tubing, is it constant or not? It's constant, right? Because we're saying steady state. Whatever enters here, leaves here. You have no accumulation. Otherwise, you will have some accumulation. Let's say it will have more and more gas, or it will have some, like an emptying process. You will have less and less gas with time. So we are saying the amount of mass in this volume with time doesn't change. Okay? You always have the same amount of mass that comes in and comes out. That means the mass flow, okay, is constant along the tubing. Now, the mass flow in this location, right, at the inlet of the tubing, is equal to the density of the gas, okay, let's call it at WF, times this gas local flow rate, right? Yes? And the local, yeah, and then we have at the top, we have the same mass flow, density of the gas at the wellhead times the Q of the gas. This is local, okay? That's not standard condition, that's local. And let's call this one 0.1 and this 0.2, such that this will be 2 and this will be 1. Okay. Now, how is the density at the bottom of the well? The density of the gas, this guy here. Is it higher or lower than the density of the wellhead? We can get, how is the pressure at the bottom of the well? It is higher, right? Therefore, if you have higher density, using the equation, the real gas equation of state, okay, density is equal to ZRT divided by P. Okay? Let's say that T is more or less constant, okay, doesn't change much. Let's assume now for a moment. If P is higher, then the density is lower. Yeah, so we made a mistake, right? What is the problem? It's not density here, but it's this V, okay? We made a mistake. And the inverse of that is the density, okay? The specific volume, the inverse of that is the density, therefore this expression is like that. Yes? Now is correct? Yeah? Okay. So when I increase pressure, I increase the density, okay? And the same thing here. Therefore, the density at the bottom of the well will be bigger than the density at the wellhead, right? Therefore, using the equation, the Q at G1 will be smaller, right, than the Q at G2. Yes? Because the mass flow is the same, okay? These two are the same. If this one is bigger than this one, therefore this one has to be smaller than this one to compensate, okay? It's like the mass flow is that product. If this one is big, this one has to be small. If this one is small, this one has to be big. Okay? Therefore, the whole story here was to tell you that the local gas rate, it does something like that. Okay? We don't have time to make this calculation in this course, but it goes something like that. From a small value, is compress the gas at the bottom of the well, and it can flow very easily. But then when pressure starts to go down, the gas starts to expand. Okay? It starts to take a lot of place. Okay? And if you remember, how do I calculate the local rate of gas? Is the velocity of the gas times the cross-section area of the pipe, right? This is the cross-section area of the pipe. Okay? The cross-section area of the pipe is the same, doesn't change. It's the same pipe from bottom up. Okay? But if here is very low, okay, this Q, that means that the velocity will be very low. Okay? But if here the Q is very big, that means that the velocity is going to be big. Okay? And that can cause erosion in the pipe. Okay? Because if you have too high velocities in some section in the tubing, you will start to take material out of the walls. Okay? You start to make erosion. And that causes an integrity problem in the tubing. If you have a hole in the tubing, then you will have to change it in time. Okay? So the whole point of this discussion is to say you want to select a tubing size, a tubing diameter, such that you don't get erosion for the rate that you want. Okay? It has to be big enough such that the velocity will be low enough and you don't get erosion. Okay? For that, so let me just make that summary here. So select a diameter such that we don't get erosion in the tubing. Okay, so the velocity of the gas, and it's usually the highest is at the wellhead. Okay, because of this phenomena I showed here, usually the highest occur always at the wellhead, has to be less than the erosional velocity. Okay. And for that, I just want to give you a reference. If you're interested, something that you have to do in the future is the API 14E. Okay? API stands for American Petroleum Institute. Okay? And 14E is a recommended practice on erosion. Okay? How to evaluate erosion. So you have some wave, you have gas, but if you have sand, so you have to calculate an average density because the sand is making bulk. But just to make you aware of that, that's something we have to take into account when selecting the size. Okay? Another factor we have to take into account is liquid loading. Okay? Normally, if you see, we are going to put our tubing here. Okay, we're going to put our gas flowing up. Okay, normally we don't have only gas in the tubing. Normally we have some liquid. Okay, and the reason why we have sometimes liquid, it can be two sources. Okay, it can be condensate. Okay, if we look at the phase diagram once more. Okay, that we discussed yesterday. Okay, that's the phase envelope for a gas. So we have our gas initially at reservoir pressure and reservoir temperature is there. But when it flows through the tubing, that pressure and temperature are reduced, they will enter into the two-phase region. So you will start having some condensate coming out of the gas. Okay, and that condensate is simply some liquid, okay, that starts to come out of the gas. Another source of liquid is water in solution. Okay, water dissolved in the gas. And in the, if you see, you make a zoom on the reservoir and you look at what happens there in the rock, you have, let's say, something like this, okay? You have a bunch of grains that are tightly packed, okay? Maybe we can make it a bit bigger. Okay, and usually around this rock there are water wet. Okay, you have some water that is wetting and is around the whole rock. Okay, no matter which formation, no matter which, it's usually the most typical case is that you have some water wetting the grains. Okay, you have some water wetting the rock. Okay, and in between you have the gas, okay, or oil. In our case we are discussing gas. Okay, so that is gas and this is water. Okay, with all of that time, all of those, millions of years that the gas was there in the reservoir, there was some mass transfer starting to happen between the water and the gas. Okay, part of the water came into the gas and just stayed there. Okay, it's now in gas in vapor form. Okay, so when you take it out and you start reducing pressure and temperature, something like that happens. That water starts to condensate, starts to come out of solution. Okay, it's like when you see in the morning that on the windshield of the car that gets sometimes a bit wet. The temperature dropped, and then because of that, you have water dropping out of the gas. Okay, it's the same thing. Okay, so that liquid can be a big problem because you have to take it out of the well. Okay, you cannot. That liquid has to. Everything that enters has to come out of the well. And that liquid, if we take a zoom at how it looks like, let's take a droplet of that liquid. Okay, that liquid is pulled up by the gas, okay, by the drag of the gas. The drag, if the gas is flowing around this droplet, okay, and is making it go up, okay. So it's making the velocity of this droplet, okay, is going up because of the gas. Now, what happens if that velocity is not big enough? It cannot lift the droplet, and the droplet simply will fall on the tubing. And it will start, that's a big problem, because it will start to accumulate. Let's look at our well now. Okay, we have here our droplets, okay, of water or condensate, whatever it is we have. And then if they cannot flow up, they will start to go down. And they will start to fill, okay, and fill. And maybe at the end, I will have a big column on the accumulating on the well, okay? The problem there is that creates a hydrostatic pressure against the formation, okay? So not only that you have liquid accumulation that you're not taking out and is going to increase with time, okay? But at the same time, it's creating an additional back pressure against the formation, okay? So that's what we refer to as liquid loading. Okay, liquid loading, so accumulation of liquid in the wellbore. And second, we also have an additional back pressure against the formation, which reduces the rate, which brings the rate down, okay? And that's bad. So we have to make sure that we select that velocity of the liquid depends on the diameter of the pipe, okay? So we want to make sure that we use a small enough pipe such that the velocity is high enough to lift these droplets if we have liquid, okay? So the whole point here is select the diameter of tubing such that the velocity of the gas is high enough to lift the droplets. Okay, droplets of liquid. For that, there are many different criteria. People, believe some different things, but basically we have the most famous and most traditional criteria is the criteria of Turner, okay, the Turner equation. From there you calculate the minimum velocity. It's like you make a force balance on the droplet. You have a force of drag coming up. You have the weight coming down, and then you have the buoyancy. Okay, and Turner, what he did, he balanced all of these forces. Okay, and then he said, well, the minimum case is when all of them are zero. Okay, in reality, it should go up, but the minimum is when all of them are zero. That's when it will start to come down. So there, with that, he found a critical gas velocity, and he say my gas velocity has to be greater than that critical number. Okay, we are not going to talk more about it, but just to make you aware of that. Okay, so far it's not so easy to define tubing size. Okay, we need to take into account minimize delta P, maximize rate, the cost. If we use a big tubing, it will be more costly, our well will be more expensive. Avoid erosion. We have to make it big enough such that we don't have erosion. And liquid loading, we have to make it small enough so we don't get accumulation. And there is one more thing that I'm going to discuss here, which is the tubing hanger. Okay? The tubing is usually at the top. I always make this figure. Okay? And you have something that is holding the tubing. All the weight of the tubing is held by these two guys, okay, these two things that I have here. And the way, if I want to make a very simple sketch of how that looks like, okay, that looks something like that. And you have some sort of a disc, and you have the tubing is threaded in the center and goes down. Okay, so this thing, let's see how to make it. It's something like this. Okay, and here I have a hole. That's what we call the hanger. Okay, the tubing hanger. I thread it or I do some other way to fix it to the tubing, and then I just lay it down on this part. Okay, I lay it down such that it will rest on the casing. This part is the shoulder. Okay, the landing. This part here is the landing shoulder. Okay. So if I have, first I have to make sure, okay, that the hole I put inside is enough such that the hanger, okay, this part here, will have enough structural, it will be strong enough to hold the weight of the tubing. Okay, has to be thick enough, the pipe, the size has to be small enough such that it can still hold the weight of the tubing. Another thing is that I don't only have the tubing is not the only thing that is passing through that hanger. I typically make some other holes, okay? And these other holes, they are, one of them is to put a hydraulic line, okay? I put a pipe, okay, or a small pipe, a hydraulic line, and that comes to a position in the tubing, okay, where I have the downhole safety valve. okay, that we need to have on the well. It's usually 100 meters to 200 meters below the wellhead. Okay, let me see if I can show you a figure. Okay, it's here. Just let me open it with the other. You see there? Okay, so in normal position, it's like that. Okay, and you cannot see it. Okay, you see that there is a pipe. Okay, that is just close, just all the way down. Okay, when for some reason something happens to that line at the surface, okay, you see that it lost, I will show you now what is up there. But the pipe starts to go up, okay, you have a spring that is pulling up, and then that flapper is just going to close the well. Okay, so let me see if I have it maybe here. So this, where do I have? Yeah, so is like a safety valve, okay, such that I have to have pressurized, I have to have pressure always there, such to keep it open, and then to have flow of hydrocarbons. If something happens here, there is an accident, someone came with a crane and knocked the Christmas tree, then that line is going to be broken, okay? And that what ensures is that there is a spring that starts to pull the inner pipe up, okay? And then you have a flapper that simply closes the well. Okay, such that you don't have any leakage, you don't have any problem of explosion, and so forth. Okay, let me see if I find another figure. Which shows better. Just from a different course, but see if we have that discussion here. Okay. Okay. You have an inner pipe that can move up and down, but here you have a spring that is compressed. Okay, and you have that hydraulic line that is keeping it down. Okay, keeping it such that this flapper is covered. Okay, if for some reason something happens to the hydraulic line, an accident, whatever, okay, that spring is going to push this piston up, okay, this pipe up, and then this flapper is simply going to close. Okay, and then you won't have, then the flow from the well will be simply closed, secure. Okay, so I'm going to put that drawing here for in your notes. Okay, so we have to make room for that line, okay, for that line, and we have all kind of other things. Sometimes we want to send to the well, okay. We want to maybe make a port, another line that will be for some things are if I have a downhole pressure gauge, okay. If I want to measure pressure, sometimes I put a small instrument all the way down, but then I have to put a line, okay, to receive the signal. Then sometimes I can have some chemical injection, okay. Okay, we're going to talk a bit about that later, but scale is a problem in scale inhibitor. Is a problem in gas wells. Scale, like what you get in the faucet in your home, okay, that starts to get white. Okay, you can get the same thing, the same accumulation of scale in the tubing. So you inject something that avoids that, it will start to stick on the walls. You have other things you can have. If you have a pump, you have power cable, etc. You can have many things through that port, okay? And because of that, that port starts to become less, it will have to less and less space, okay? So depending how many lines you have to make sure that the size of tubing you have, gives you enough structural resistance to that hanger to be able to hold the weight, okay? So let's make that here. So phi of the tubing has to be small enough to allow the tubing hanger integrity. Okay, I want to make it small such that the collection of all the other lines and everything, still the hanger has enough strength to hold the weight of the tubing. Okay, so now we finish with how, what things do we have to take into account when deciding on the size, okay, of the diameter of the tubing. Another thing I want to discuss here is the effect of wellhead pressure on the equilibrium point. Okay. Okay. Here I have QG, here I have PWF, I have my IPR, and then I have my TPR. Okay. And we have, let's refresh my system. Okay, and I have my separator. Let's think for a moment that we can change separator pressure. Okay, let's say that we can change it. This one is at P wellhead pressure 1. What happens if I increase the pressure at the wellhead? Somehow, I increase the pressure at the separator. Which curve is going to be affected? The TPR, right? That's the one that has, I started from here, that pressure, and then all the way down. Okay, so that's the one that contains that pressure. Now, do you think if I increase it, I'm going to get more rate or less rate? Less rate, right? Because you have a higher back pressure, and then that's causing, it's more difficult to flow against it. Okay? So, but now I ask you, what happens with the point at the origin? Remember here we have no flow, it's simply hydrostatic, right? So you have one case where you have P wellhead pressure 1, and you had this pressure, let's call it star, okay, with no flow. Now you have another case that you put P wellhead pressure 2, which is greater than 1. How will this P be? This P double star? is going to be bigger, right? If this one is bigger, okay, then the density is bigger, then therefore that pressure has to be bigger. Okay, therefore what you are doing when you are increasing the wellhead pressure, you are actually shifting the curve up. That's TPR but with wellhead pressure 2. Okay, it's like a shifting effect where PWH2 is greater than PWH1. Okay, remember, very different from the tubing size. Tubing size is like pivoting. Okay, you're pivoting the TPR around the same point. You increase you increase the diameter or decrease the diameter. It's pivoting. In this one, you are shifting. Okay, shifting up or shifting down. What happens if I reduce wellhead pressure? I'm going to get more rate, right? Therefore, it's going to be shifting down. TPR with PWH3, which is less than PWH1. Okay, and we have one last thing that we said yesterday. Okay, so effect of depletion on the flow equilibrium. Okay, we have our IPR, which looks like that. We have our TPR, which looks like that. Okay, PWF. Now, what happens when PR goes down? What curve is going to be affected? IPR, that's correct. So if I reduce the pressure, how is that curve going to change? If I reduce reservoir pressure, the reservoir has less energy, right, to flow. Therefore, the rate will be reduced. Okay? Therefore, it looks that we have done yesterday, right? It will look something like that. That's IPR for PR1, that's for PR2, for PR3, when PR3 is less than PR2 is less than PR1. Okay? So the equilibrium point, think about that way, the reservoir has less energy, therefore it can flow at a lower rate. Okay? So with time, it will go and follow that line. Okay? Down and down and down. Okay? Or what we discussed yesterday in class, if you have a fixed rate, right, that you want to produce, it's not very good to do it on this plot, right? Because here this is bottom hole equilibrium. We control the well is with the choke, which is at the wellhead. So we should make a plot, if we are going to discuss about choke, we should make a plot about wellhead equilibrium, okay, not downhole. Be careful on that. But the point is, if I'm operating with a fixed rate, I will need to choke, but then with time, the choke will become less and less and less. That clear? Yes, so effect of tubing size, effect of wellhead pressure, and effect of reservoir pressure. Okay? Okay. So I just want to have a short discussion on the separator. Short, let's make a new page. Separator. Okay. And the separator is receiving the well stream, right? So gas we paint with red. And liquid, sometimes we can have water and oil. but let's paint it with green, which is like an oil. And then we have two lines coming out. So how do I ensure, we're saying the separator always keeps the pressure constant, okay? So how do I ensure that that's the case, okay, that happens all the time? I have two types of control in the separator, okay? One of them, I stick a pressure measurement here, okay? And then the other next step is I stick a level meter here, okay, which is measuring what is the level of my separator. Okay. And after I take those measurements, I put some control here. So I add one valve, control valve, for the gas line, and I add one control valve for the liquid line. Okay. So the liquid valve is going to be controlled by the liquid level. Okay, if I know that the level starts to go down, then I just close the valve. Okay, I don't take too much oil. If I say that the liquid level is starting to go up, then I open that valve. Okay, I start to drain more liquid from the separator. And with the gas, I do exactly the same. Okay, with the gas, I have a controller. Okay, and here I should have, in control, we always have a set point someplace. Okay, so we have here a set point, a desired pressure we want. And here we have also a set point that will be the level, okay, the H that we want. Okay, so if the pressure starts to increase, this one will open the valve and some gas will come out to keep the pressure constant. If the pressure starts to decrease, then that one will close to keep, the pressure constant. So that's how the separator keeps a constant pressure, okay, just by this control strategy to the exit of the liquid and the exit of the gas. Okay, and these are changing all the time depending on the rates that I have. Okay. If I have variation on the rates along the life of the field, that's how I control it. Okay, so that was a short comment on the separator, but now we're going to go to something else, which was the flow line. Okay, how are we going to model a flow line? And a flow line, in principle, I can model it just like a section of tubing. Okay, if you remember the tubing equation, CT P1 minus P2 to 0.5, right? We made it for a tubing, but we can use that really for any piece of pipe, okay? We can use that equation for any piece of pipe, it is inclined or whatever, okay? We can use it for... So the way I'm going to change the equation, I will just say simply QG will be C flow line instead of tubing, okay? P1, okay, or P in squared e to the s minus P2, P instead of P2, we're going to use P out squared 0.5. No problem. We can use exactly the same equation. Okay, after all, it's just a piece of pipe inclined. Now, what happens if the pipe is horizontal? Okay. For many cases, we can just simply neglect the elevation. Okay, the elevation the elevation change for a tubing is very significant. Okay, it can be 3,000 meters, 2,500 meters. But for flow lines, sometimes the change is not very much. Okay, you have transportation along a flat area. Okay, so if the pipe is horizontal, I have to simplify that equation, okay, such that to make that. So let's go back to previous class to see how the equation looks like. Okay, looks like that. Okay, and as we are going to see, we have some issues here. Okay, so first, what happens if the elevation change is 0? Okay, what happens with S? S, if H is 0, right? The 2 points are in the same height, then H will be also 0. Okay, that means that S is 0. So far, so good. So S doesn't exist. So this one will be simply P1 minus P2. E to the 0 is 1. Okay, so I have simply P1 minus P2. Now, what happens with CT? So let's put first that comment here. S equals 0, then we are getting P in minus P out, 0.5. But what happens with CT? Okay, and CT you see it's here, okay? CT you see, all of that remains the same, length, diameter, that doesn't change. But the problem we have is this guy here. What are we going to do with that guy? Okay, and let's see what part of the problem is. So we have CT is a constant, okay, times S e to the S over e to the S minus 1, okay, right? So what happens when S equal to 0 to this expression? S, so that will be 0, right? E to the S, that will be 1. And here we have 1 minus 1, so that gives you 0 over 0. Okay, we have a problem. Okay, that's undefined. Okay, so to overcome this problem, you remember from math, long time back, maybe kindergarten, something like that, when we say what happens when we find a problem like that. Okay, when we have a problem, two things that are undefined, either infinite over infinite, 0 over infinite. You remember this guy that saved our life in math? No? L'Hopital? You know him? Well, L'Hopital, okay, a French guy, he said, if you ever find that problem, okay, if you say the limit of an expression, okay, fx, when x tends to 0, if that is undefined, okay, he said, well, you have to just derive the expression above and below. Okay, that's the same as the limit of that function, okay, is the same to say that is the limit, if I have, well, let's say two functions, gx, of f prime, g prime, when x tends to 0. If you still find problems, you can make another derivative. You can take the second derivative of that. Okay? But if we do that only once, okay, we already solved this issue. Okay? So we get s times e to the s, okay, plus e to the s divided by e to the s, right? If we derive up and down, okay, we're going to derive the upper part with respect to s, and then we derive the lower part okay, and that's going to give me this number, and if I now substitute is s equals 0, then you're going to get 1 over 1, and that gives you 1. Basically, that term disappears, so you get just the constant for the CT, for the CFL, okay? Okay, so that's how we got rid of that problem with this French guy, L'Hopital. Okay, so finally the equation is QG equals CFL P in squared minus P out squared to the power of 0.5. So now I suggest we make the exercise, okay, so now we have next exercise, that we're going to take exactly the file that you were working on yesterday, okay, we have our well, PR, PWF, remember, P wellhead, no choke, okay, but now I have a long flow line that takes me to the separator, okay, and I just want to find the project engineer told me you have two choices. You have this flow line, which is cheaper, or you have this flow line, which is expensive. Just make the calculation and see which one do you prefer, okay, for equilibrium. Okay, so we have to add that, and I suggest we make equilibrium here at the wellhead, okay? So, because we already have this curve, okay, we already have the WPR, okay? And now we just have to go from the separator with the flow line all the way to the well. So if we go to the Excel file we had yesterday, it's this one. Okay, that's what I have from yesterday. We had WPR, yeah, so here you see you have the equation for the flow line, okay, which is missing the 0.5 at the top for some reason. Okay, but here you have the coefficient of the flow line, one flow line. So what was the meaning if which one is more expensive? This one, 1.25 e to the 5, or this one, 4 e to the 4? What do you think? What did we say about the diameter? Okay, if you look at the expression for C, okay, for CT, it has CT is all of this guy, okay, all of that, okay. So if the diameter is bigger, this C is going to be bigger, okay. Therefore, here most likely the most expensive flow line is the one that has the biggest C, okay. Biggest C for the same delta P. If you look here, if I have a big C for the same pressure numbers, I'm going to get a higher rate. Okay, therefore is when I make my pipeline big. Okay, so let's now let's say WPR. I think we still have it here. Okay, we can get rid of this. Yeah, let's leave it there. Just remember that's for reservoir pressure 304, and this is for 200. Okay, but now we don't have to intersect simply with separator pressure, but we have to intersect with the flow line, okay, with the available pressure at the inlet, no, the required pressure at the inlet of the flow line. Okay, for that, I suggest we create another column. Where do we make it? Maybe here. Let's simply call it P in, okay? That means the pressure at the inlet of the flow line, and that will be in bar. Okay, and now let's see which equation are we going to use. Okay, we punch Alt F11, and so we have it, I think it's in module 1, and we're looking for tubing, IPR, none of that, but we have line, okay, either flow line, pipeline, is just a piece of line. Okay, this one gives you the rate that we don't need. Okay, this one gives you P1. Is that the one we need? What do we need, P1 or P2? P1, Y P1, Y P2. Okay, let's go back to our equilibrium, okay? Very important. That's my point. I have to move from here to here. I have already done that. That's this curve here. Available pressure at the top of the well, at the wellhead. Okay, now I have to move from the separator all the way to the wellhead, counter current. So if I see the flow line, okay, let me extract the flow line. One and two, okay, that's my flow line, and the flow is going on this direction. I have this pressure, okay, I have two, which is P separator. Okay, so then I want to calculate P1, which is the pressure at the inlet of the flow line. Okay, so that's the equation we have to use, line P1. Okay, so let's use that. Here we say P in will be, we find that function in user defined with L, line P1. Okay, and I'm going to let's use the one which is the cheapest, okay, just to see what is the difference. So let's use this one first. I block it with F4, okay, then P2 will be separator pressure, 40, and I also block it. And then the rate, I want to use the same rate that we were using before, and I think it's this rate all the way in E, okay. For zero rate, of course, is horizontal line, so I get the same pressure, okay, both sides. 40, and then I have all the way to 86. Okay, and then I'm going to plot it. And I'm going to call it FPR, okay, which stands for flow line performance relationship. Or I can call it PPR, pipeline performance relationship. In the X I have the rate, and in the Y I have the P in. Yeah, just save it and close it and open again. Yeah, save that file, open and close. Yes, close and open again. Who has the memory stick? Here. Okay, thank you. Does it work? Okay, those of you that finished, you can make, I say, add one more column. So here we say small pipeline, and let's make one that says for the big pipeline, just to compare them, okay? And we're going to use again the same equation, line P1, but now we're going to use the coefficient for the big flow line, okay? Just to see what is the change in our equilibrium point. So maybe here I want to change the name for Okay. So that's what I got. I think most of you got the same. I have the green curve that we have calculated yesterday. That's the wellhead performance relationship. Or in another way, that's the available pressure at the wellhead calculated from the reservoir. Okay, when reservoir pressure is 304. Then we have separator pressure. If there was no flow line, okay, simply make the intersection between the green and the violet. Okay, that we have done yesterday. Then we have the two flow line, or the two pipeline. I call it pipeline performance relationship, but basically is the required pressure at the inlet of the flow line to be able to produce that rate. Okay, and you see you have big and small. So if you see the big one, it seems that it's slightly too big, right? It's like no having no pipeline at all. Okay, if you see here the difference between that at a constant pressure, the rates are extremely similar. Okay, that's an indication that that pipeline might be slightly oversized. Okay, while that pipeline, it gives you less rate, but it's not, significantly less. It's a bit less. So I would say you have to maybe find something in between, but the big pipeline is definitively too big. Okay, if you go on another time, now we see this WPR at 200 bar, you see that the difference becomes smaller. Okay, in that case, at the later stage in the field, it really doesn't matter if you use big or small pipeline, both of them give you the same. Okay, so that's sometimes a challenge in field development. Okay, we make a design for the initial phase, but it should be also good for the later phase. Okay, and vice versa. Um, I want to make also a comment about pipeline sizing. Just like what we have done for the tubing, okay? Pipeline sizing, we have a few things that we have to take into account. One of them is, just like in the tubing case, minimize delta P, right? And then that allows you to maximize rate. Okay? The other thing is the cost. Okay, and usually if you have a very long pipeline, if you make a small change in diameter, that can give you a significant change in the price, okay, in the cost. If you use a bigger pipe, it's more expensive to transport, it's more expensive to weld it, it's more expensive to lay it down, it's more expensive to install it. Okay, so the cost is a big factor that we have to take into account. Of course, we have the erosion, okay, considerations. You have to make sure that you are using a big enough pipe. But there is one more, and it's not about liquid loading, but it's about liquid accumulation. And that happens if you have, let's say the pipe might be undulating, okay, it's following the terrain, it's going up and down, up and down. And if the gas has with it some liquid, okay, typically it's going to accumulate, okay, in the lower points of the system. Okay, and if it's not, the gas is not able to retrieve it in time, okay? Then it's going to just fill up and fill up and fill up, okay? Until it maybe creates a blockage, okay, of the pipe. In that case, the pressure here of the gas cannot flow anymore. Therefore, it will start to increase, okay? At that point, if we see at the pressure, okay, with time, the pressure was here initially, then it will start to increase, 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 until it's enough just to blow, to push all of that slug in the way, okay? And after that, will go down, and then again it starts to accumulate, goes up, and then blows down. Okay, so we have some sort of cyclic behavior. Part of the problem is that if we measure here, let's say we have at some place, at some point here, we have a separator. Okay, and we're going to measure the amount of liquid that that separator is receiving. Okay, so initially it has a very low amount, but then you get a big batch of liquid that was just the plug that was pushed by the gas, and then goes back to having very little liquid. Then you have a big plug of gas, of liquid, then goes down. And that's very challenging for the control. Okay, the control that we were discussing before for the separator, okay, has to be, this one works if the variations are very slow. Okay, but if you get all of the sudden a batch of liquid, okay, this controller is going to, it has to act, it cannot act quick enough. So let me maybe show you, if I don't think if, let's see if it's, okay, that's something else, but let's see. Flow line riser, I think it's here. You're going to get another professor. He's going to come in January, I think, and he's an expert in multi-phase flow. So he's probably going to show you some more, okay? But here you see the gas is in red, the liquid is in yellow, okay? And you see here there is no gas passing, simply the pressure is starting to increase, okay? You see slowly, slowly, it's pushing that column of liquid up, okay? That comes from the well, and here you have the facilities, the ship, okay? It's almost getting up, almost. Just be careful, now it's coming, almost coming, okay? And you get the batch of liquid. Okay? Yeah. So in a sense, that's what happens when you have gas with liquid, with some significant amount of liquid. You're going to get that, and that's extremely challenging to deal with. Okay, this behavior is what we call liquid accumulation, and that causes liquid slugging. Okay, slugging we say when there is intermittent flow of gas and liquid. Okay, so we have to design our flow lines, okay, with a small enough size such that the gas is able to push that liquid out, okay, that you don't have too much liquid accumulation, okay, to avoid. Of course, that, you know, I cannot understand what I wrote here, accumulation, okay? Of course, that's a challenge, okay? Because at the initial time, you have a very high rate, but then when the rate starts to go down in the field, you eventually, the diameter won't be big enough, and you eventually will have liquid accumulation. So this is a very typical problem on a late life of the field, It's not something that usually you can avoid. Okay? Because simply if we make it too small, then at the beginning I'm going to choke production. I'm not going to get the production that I want, but it will be good, later. If initially I make the pipe very big, okay, so I have a good production, then I will have the problem after. So, it's difficult, and usually it is difficult to find a solution. Um, what else here? Liquids, erosion, cost. Okay, we have one more thing. That is the case of cooling. Okay? So big diameter usually leads to more cooling. Okay? And there are a few problems with cooling. If you use a bigger diameter, that gives you more area for heat transfer. Okay? Remember that we are exchanging heat with all of these surface. Okay? That's a Q that is coming out. And if I have a big pipe, then I will have a lot of heat transfer. And that can cause problems because you have more oil and water condensation. Okay, that gives you more liquid, and it can lead to accumulation. Okay, it can also lead to corrosion. Okay, typically in pipelines, gas pipelines, if you have condensation sometimes occur at the top of the pipe. Okay, condensation of water. Why? Because sometimes the pipe is buried, okay? And then the coolest will be inside the ground, it is shielded, okay? But close to the top, you have kind of the lower temperature, okay? Therefore, condensation tends to occur at the top. And when you have condensation of water, then you have some spot of corrosion, okay? If you have water, then you can have corrosion on the top. That's called TOL corrosion, okay? Top of line. Okay. Then also, you can have some problems, what we are going to discuss later, called hydrates. Okay, if the temperature is too low, you can have hydrates. You can also have some other issues, like for oil flow lines. You can have wax. Usually also the viscosity goes up, okay, so then you create more pressure drop in oil flow lines. So I like to keep the heat as much as possible on the pipe. So if I make a very big diameter, that can cause some issues that we're going to look more in detail later. Okay. Do you need a break? 10 minutes? Yes? Okay, so let's take a break, 10 minutes. See you here let's say 8:50. Okay? So what I want to focus now is on field production scheduling. Okay? To try to calculate how much, or define how much the field is going to produce, and to calculate the field production profile with time. So that production scheduling, we say, is calculate or estimate, define, calculate, and estimate the field production profile with time. Okay? And I want to do that with an example. Okay, we already have all the basic tools we need. So we are going to do it with an example. But for that, we are going to need some introduction. We are going to do it for Block 2 in Tanzania, offshore. Okay, we're going to use the data from Block 2. So I want to give a short introduction on that. Let's see, I think I have some image. That's not. Okay, we're going to talk later about the okay, so as Tanzania, typically the government, I think it's not TPDC, but it's the Ministry of Energy. How do you call it? Energy and Petroleum or Minerals? Here? Energy. Okay. Nothing else? Ministry of Energy? Okay. Okay, so they divide Tanzania, where you have prospects of oil and gas, into blocks. Okay, and then each company can apply for a production license, okay, in each one of these blocks. And you see you have here some players. Shell is taking the blocks at the top, then Petrobras, and here you have block 2, okay, which is where Statoil, now they're called Equinor, is located. And I think that's the most in short sight, that's the most, it will come soon in the future, that development. And the field we're going to be looking at, or we are going to be doing planning for, is, yeah, I think we have, before going to that, I think there was here, okay? We have different discoveries on that block. It's not here, here. Okay, we are going to, I think the example I have is only with Labani, Tangawizi, and Safarani. I don't think Giligiliani and Mronge are going to be, I don't think they're going to be produced, I'm not sure. But the example I have was made actually as of part of it, a student of mine was working on that 2 years ago. And yeah, so the way the field is going to be developed, okay, is quite deep. The area on the field, I think, is around, the water depth is 2,200 all the way to 2,600 meters, okay, which is quite deep. And I think I have some more pictures of the topology of the field. Okay, so that's all the way to shore. So what you see there, the topology, that's the topology of the seabed. Okay, here you have shore. That distance from here to here, I think is like 85 kilometers, or something like that. Okay, the distance from here. Okay, is like yeah, maybe a bit less than 80, but around 80 kilometers. Okay, and the way it's going to be developed, this field, is subsea wells. Okay, you're going to have subsea templates. We're going to talk a bit about how they look like. But here you see Labani, Tangawizi, and Safarani. Those are, you see some points. I'm not sure if you can see very well, but there are some points inside each. The yellow contour That's the reservoir, okay, marking the reservoir. And you have some points inside that are the wells, okay. And after that, you have some flow lines that go and take the production to shore. Okay, so here you have Labani, Tangawisi, and Safarani. And you see, so first, something interesting to see is that I think the slope is slightly going up towards shore, but you have some, you have some valleys, it's crossing some valley here, and then here you have a big jump, and then it continues further to shore. Okay, I think I have one more figure, okay, that shows more in detail. Okay. And here you have, so you have service, the flow line is the red one, okay? So you have here kind of a loop that goes around all of these wells, okay, in Safarani. And then you have another line that goes and take the production from Labani, Safarani, Labani, and Tangawisi. Yeah, so Tangawisi is not shown here. So I think it's only producing from Labani and Safarani. Safarani. Yeah. We'll see now. I think I have a better drawing later, okay? But we need a few things, and that's what we're going to discuss now. So the idea is that the production will be taken to here. They're going to place an LNG plant, okay? Remember, gas, you need to have a customer, okay? The appraisal or the analysis was that they want to sell it to Asian markets, okay? Not for internal use, but they want to sell it for Asian markets. And so they cannot do it with pipeline, okay? There is no gas infrastructure from Tanzania to other places. So they're going to build an LNG terminal such that you can convert the gas to LNG, liquefied natural gas, and then you can transport it with tankers all the way to Asian markets. Okay, so that's the plan. And that's very similar. We have a field in Norway. Norwegians, like this idea, and they propose this idea because we have a field in Norway called Snow White, okay, or in Norwegian, Snøhvit, okay, white snow, that is exactly produced with the same concept. Okay, this concept is called subsea to beach. Okay, I don't have anything, any platform, any FPSO that we're going to cover maybe tomorrow. Anything, we just have everything is on the subsea, and then I put a line all the way to shore. Okay, and then I have onshore, I have two things. Okay, first I have a special type of separator that is made out of multiple pipes, okay? So, onshore facilities, okay? We have a slug catcher, okay? Remember what I explained later about slugging, before about slugging? You have something that is called slug catcher. It's like a separator, but it's made out of a lot of long pieces of pipe, okay? You make one long pipe, and then you make another long pipe, and another long pipe, okay, and so forth. And then at the end, you start draining the liquid, okay, from that pipe, okay, and the gas continues on that side. Okay, but basically it's to split. I don't going to use a vessel anymore. The separator that can be 6 meters, can be 4 meters long, and 2 meters or 3 meters wide. What they use is a long section of pipe, such that when you have a slug, you have enough space to fit that slug. Okay, you have enough length to fit that slug, and it's not going to bottleneck your So that's how it looks like, a long connection of pipes, and then you have drainage. I think it might have, let me see if I have a video. I think I have. Let's see if here they have a nice picture. No pictures, okay, just, okay. Okay, different designs, different things you have to put, but it looks basically something like that. You have a big inlet manifold that distributes it. You have then separation, and you take the gas on top and you collect the liquid at the bottom. Okay, so I think that's a nice figure. We can copy that. Okay, but the idea is that you have more volume than what you will have on a separator. If you want the separator to take that liquid, it will be very big and very wide. Okay, very long and very wide. You do it with pipe, it's cheaper, but you can put many pipes, and then you take into account you have extra volume to take all that liquid that is coming out at once. Okay, and that's because we cannot avoid slugging. Okay, in that case, they try different things, changing the rate. They say no, there is no point. We cannot avoid slugging, so we have to have this slug catcher. And I think it's the same in block 2. Okay. Then after that, I have the LNG plant. Okay. That basically is cooling methane, or cooling the natural gas until it becomes liquid. And I had another figure here. Okay, that's from the field in Norway, but I think they're planning to do exactly the same here. Okay, you have the slug catcher, you have all kind of things, but you have all the facility where you make LNG. Yep. And you have there some place. That's where the tanker comes and loads the LNG in the tanker. These tankers are the ones that have like a sphere on top. They look like a sphere, and then they transport it to the Asian market. Let's see if I have. I think I have. Okay, you have a bunch of processes that happen in the plant. You have to take out the liquid. You have to take out to make the gas very lean, because if you start having condensation, okay, of anything, water, and you put it at low temperatures, it's going to freeze. Okay, you're going to have a blockage of ice. So they have to make sure that they take all the impurities, that they take all the condensate, they take all the heavy components, that they take the liquid before they can start to make the cooling. And here you have the LNG storage and LNG transport. These are the ships that I was telling you about, that they look like that. Okay. Let's see, do we have something else? No, that's something else. Yeah, well, not very important. Okay, so that's our field, and that's what we are going to calculate. Okay, we are in the, let's say, in the design phase. We know the volumes, we know the pressures, we know the properties, we know more or less the reservoir properties. So our task in this point is that we are from the reservoir and production team, and we want to calculate how much that field is going to produce with time. Okay, and we have some pre-contract made with some customer. They say we need 18 million standard cubic meter per day, okay, of LNG, of gas. That's the production we need. So we have to find out to calculate for how long we'll be able to produce that rate and what happens after plateau. How much is the post-plateau production? Okay, so that's our task. Okay, let's put here. Okay, that's a contract for a fixed amount of gas. Okay, that will be 18 million, I think, standard cubic meter per day. Yeah, you're committed, okay, to deliver. And I think that the contract is quite long. It's, I think, more than 20 years, okay, that we have to provide. Then, so what we are interested is the plateau length, okay, that we are going to use our analysis for that, what we just covered now. And then we need also the post-plateau production profile. Okay, here plateau length, here we have to find basically that's choke, okay, when we are choking to control production. And after the post plateau, that's basically we have open choke, okay. So we are operating here in mode A, and here we're operating in mode B, okay, what we discussed before. One is plateau mode and the other is potential. So those are the things that we want to calculate. We are part of the team to try to compute, how much it will be. Okay, now I want to I maybe want to say something about how are the wells arranged, okay? Just about the subsea architecture. Subsea layout, okay, sometimes we call it subsea architecture, and that is how wells are arranged. But for that, I think if we may take a small detour, a short detour, and we are going to talk about production manifold. Okay, so let's talk about production. There is a very central, and then we are going to try to adapt it for our field, okay? There is a very central production manifold, a very central unit in the field, or a central component of the field, that is called the production manifold, okay? And the production manifold has a few functions, okay? One of them is to route the production of wells, okay? If you want to send the production to one side or another, you have to choose where to send the wells. You can do that with the production manifold. Most importantly, you can test the wells, okay? It allows you to perform testing of wells, okay? And that's very important for what we call allocation, okay? Allocation is basically to know where is the oil or the gas coming from, okay? To try to determine the source, okay, of gas, of hydrocarbons, of gas and oil, okay? Why is the source important? If you have it's important for different reasons, okay? But one reason is to simply split, okay, split the profit. For example, between partners. If you have different partners in a field and some wells belong to Shell, some of them belong to TPDC, some of them belong to Equinor, to Statoil, you want to find out how much from all the sales that I have, how much do I have to pay each one of them, okay? So split profit is extremely important and is one of the main reasons we make testing, okay? If we have a field, let's say, okay, we have 2 wells that are producing to a separator. We want to know how much is the production of well 1 and how much is the production of well 2. Because this rate that we are selling of the field, we at the end we have to convert back, okay, to pay back. Let's say this one is the owner is TPDC, and this one the owner is Equinor. Okay, so we have to know how to split the profit. Another very important reason we have is to improve reservoir models. Okay, remember these models are very uncertain. Okay, I make it assuming that you have some volume, that you have some properties, that you have some permeability, porosity, etc. Okay, when I start to get more data, I can compare. So here I say I compare the model, okay, versus the data. Okay, and let's say I'm getting, okay, if I make the simulation versus time, okay, I have the points of data that are measured, okay, and I have the points of the model. Okay, and initially the model maybe gives me fine, but then it starts to deviate. Okay, in that sense I say, well, you know, my model is not correct. There is some variable there, some assumption that I made that is not correct. Maybe the volume I put is too big, maybe the volume I put is too small, maybe the productivity of the formation is too big or too small. So I try to adjust that such that I get exactly the same measured behavior. So this can be pressure, can be rate, whatever, okay? And that process is usually called, for reservoir models, is called history matching. Okay? I'm trying to match a model with the history that I measure, with the data that I measure. And in a very simplistic way, this is the reason for that. Okay? To test wells, to split profit, to improve models. Okay? In a very simplistic way. So the manifold, I'm going to paint here, for example. Okay, let's say this is a land field. Okay, and let's say I have two wells. Okay, I have well one. Let's make it properly. Okay, and I have two separators. I have one which is the main production separator, and one that is the test separator. Usually the production has to take the production from the whole or for a bunch of wells. Okay, maybe not for the whole field, but for a lot of wells. Okay, so it has to be big. The test, it can be small because it's going to take just the production of one well. You send to test, you send individually every well. Okay, and now we have, let's say we have one well here. Okay, we're going to make all valves. Okay, we have our choke, and then we have to put something very important. Okay, if we're going to put two wells together, right, in the same line, let's say here, okay, and then we have another well. Okay, remember, master valve, wing valve, swap valve, we have to put a check valve. Okay, because if we're going to put two of these wells together, it might happen that one well has high reservoir pressure, for example, and high productivity, and this one has low reservoir pressure and low productivity. If we put the two of them together, it might happen that the big producer, the strong producer, starts to produce back into the other well. Okay, so it doesn't end up in the separator, but actually you have stealing, the other well is kind of stealing production. Okay, it's a thief well. Okay, so that's why we have our check valve, and we make it on that symbol. Check valve. Okay, now how do I connect, okay, how do I connect, okay, let's say well 1 and well 2 to production. Okay, how do I connect these wells to the production line? Okay, I use a piece of pipe simply, right? That I call, this one I call a header. Okay, a big piece of pipe. Okay, and I connect to that header, I connect this line. Okay, and simply I come and I connect each one of these wells to that header. Okay, so I come here on that header, and then from here, that is coming out. Okay, no issue. So then I combine, and then it's sent further to production. Now, what happens if I want to have the option to send a well, let's say I want to sell just one to the test. What do I have to make here? What I suggest, okay, we make, just like in the other case, right? We had a header. Okay, so let's make a header. So this header, we're going to call it production header. And we're going to make another header called test header. Okay, and we are going to connect the wells to that header. We're going to put a split at some point to have the option to connect it to one or the other. Okay, here we're jumping and we're coming here. And then from that header comes just that pipe. Okay, so we have two pieces of pipe that we have said that's the header, and then the production goes there. Now, how do I control where the well is going to? If it's going to the test or if it's going to production? What do we use to control in any process plant? What do we use to change? I want to produce from here, on this line, not on that line. What do we use? Valves, okay? So we have to put two valves, okay? One of the valves will be here, okay? And the other valve will be here. Okay, and the same thing on this line. One of the valves will be here, and the other valve will be here. Okay, such that if let's say I have to put the two wells to production. Okay, I have normal production, everything is happy, I have don't want to do any tests. So this valve, how is it gonna be? Open, this one, closed, okay? This one, open, this one, closed, okay? So then the fluid goes on the header and then goes on that direction. What happens if I want to put now well 1 to test? I close this valve, right? And I open this valve, then it goes all the way to the test header, and then it goes to the test separator. And I measure how much that well is producing. Okay. And the opposite, if I want to put well 2, I close this valve, open this valve, and then I flow to test, and then I measure how much it is producing. So let me show you a picture how that looks like in real life. Okay, so here I didn't show you, but these are some wells from the Gulf War in Hawaii that didn't have this safety valve, okay, what we were discussing before. If you have no safety valve and they were doing bombing on the field, okay, they actually, the wellhead or the Christmas tree just disappeared. Something happened, it got damaged, okay, and because of that you have no safety. Okay, they start producing and then you have a spark and then you have just a big, fire for a long time that you cannot control. So after that, that was one of the initiators that people say we need to have this downhole safety valve, okay, such that if something happens at the wellhead, something happens at the Christmas tree, we can still, the well will be closed and it will be safe. Okay, but that's not, I wanted to show you this figure. Okay, can you identify the test line and the production line? This is a field, I think, in Libya. I didn't take that picture. That was from I think it was from a magazine. But you see, here is from every well. We have a lot of them. Okay, 1, 2, 3, 4, 5, 6, 7 wells. Okay, that go up. And then, which one is the production header and which one is the test header? Production is the bigger, right? It's a big pipe, and this is the test. The test has to take just the production of one well, so it can be very small. I can save money. Okay. Where are the valves? These valves we call them the routing valves. Okay. This valve here, we typically call them the routing valves. Okay. These two here, and then I can decide if the well is going to go to production or if it's going to go to testing. Okay, like from another field, that picture, actually that's from a project that was involved in. Where is it? Here. Okay, here you have another example. That was my boss at that time. And it looks like he's making some difficult questions to the field manager who is here. Okay, but here we have from the wells. Okay, we have 1, 2, 3, 4, 5 wells. Okay, and you can go to either production header or test header, and we have our valves here. Okay, and here we have the line going towards the field. Okay, exactly the same arrangement. So the production manifold is the heart, in a way, of the production system, and it allows you to make testing or to route. If you have, it might happen also that you don't have just one production separator, okay, but you have many, because the production is very big. If you try to make just one, it will be very big, it will take a lot of space, and it will be very expensive. Okay, so sometimes if the field is very big, we try to split and put two, okay, in parallel. So then I can decide how to change the wells, to which separator they go. Okay, and I usually make it such that if I have, for example, many wells have a high gas content, okay, and some wells don't have low gas content, I try to split evenly, okay, such that both separators, they get the same amount of gas, roughly, okay, or the same with water. I try to split such that it's balanced in the separator. That here? Yes? Okay. So now what happens with subsea? Okay? In subsea systems. In subsea systems, sometimes we have exactly the same need, okay, that we need to test. Therefore, we need a manifold. Okay, so let's say I have a platform. Okay, and here I have, again in the same way, I have, so maybe let's remove the platform, even though it looks nice, okay? Let's say that we're going to put an area here, okay, where we have a platform. Or platform, it can be also a ship, can be an FPSO. What FPSO stands for? Floating. And offloading, yes, okay. Stands for floating production, storage, okay, and offloading Usually they call it ship or they call it vessel. Okay, and it's simply a boat, a ship, where you put things on top. Okay, you put your separator, you put your compressor, you put your uh, living quarters, you put everything there. Okay, but let's say there we have two separators, okay, for the same purpose. We have one big separator for production, okay, and have one big separator for testing. Okay, and here we have our wells. Okay, wells, we have two types of wells that we can have in subsea systems. We can have, there are two types of wells. We can have two types of subsea wells. By the way, are you going to have, I know you have a subsea course, right? Schedule? Are you going to have it or not? You don't know yet?
We don't know who to teach, but we don't have it.
Okay. You don't have yet the teacher, okay. I think, okay. Yeah. So these things will be covered more in detail in your subsea course. Okay, I just want to give you some basic knowledge such that we can do the exercise and you understand a bit why the reasons of things. Okay, but subsea will be covered. You have a course just to focus on subsea issues. Okay, so that should be covered in that course. Okay, but we have two types. One of them we call it satellite. Okay, satellite wells. Each well is by itself, standalone, okay? So let me see if I have I think it's easier. We can make it like a square like that, okay? But we have a subsea module where we have simply the well in that module, okay? Let me see if I think I have a picture. Sorry for that, I usually have my images in okay, something like that. We can take that, we can steal it from, I think that's FMC. Don't tell FMC that I stole the figure. Okay? But it's like that. You have a big block, okay, where you have all the Christmas tree. Remember, all the things that we have in a well. We have, if we go back, is not many things, okay? We have master valves, wing valves, choke valve, we have the check, and all of that is in a compact module, okay? That looks like that. And why do we have a panel such like that? Because you want this ROV, there is some robot, okay, that we send, and that's the one that is acting, closing, and opening things, okay? So all of this panel is to have access to all the different things that, you know, that are in the well. So, and is simply all the weight of that module. Here you have the Christmas tree and you have the wellhead, okay? All of that weight is transferred to the conductor, okay? You know, in when we drill, now is slightly, you know what the conductor is? Yes? No? Okay? You know, when we drill, in the drilling process, we make a hole, right? We make a hole, okay? Then we take out the bead, okay? And then we run a piece of pipe, okay? That we call, we can call it different way. We run a piece of pipe and then we cement, okay? Between the formation and the pipe, okay? Then we come again with another bead, okay? Then we make another hole, okay? Okay, then we take out the bead, okay, pull it up, and then we run another piece of pipe, okay, and then we cement once more. And we repeat over and over and over again until we reach to the formation. Okay, so actually when I put the well like that, okay, when I draw the well exactly like that, okay, what you're actually looking here is just the last casing, okay, the casing that has contact with the formation, okay, but on top of that you have many layers of pipe that go like from outside in, okay. So the first pipe that we locate here, the first one, when we make the first hole, that's called the conductor, okay. It's not called a casing, but it's called the conductor. So the first pipe that is placed in the hole, okay, that's what we call the conductor, and it's a big pipe. It's 36-inch, and the main function of this pipe is to transfer all the load to the soil, okay. It's such that you can hang things on that pipe, okay. You have the conductor, then you run another pipe inside. The conductor has here at the top, it has like a wedge, okay. Then you put another pipe inside, and then you hang it on that wedge, okay. Then you go with the other pipe and you hang it on the one before, okay. And all of the casing strings and the tubing, they are laying the weight on the conductor, okay. So this conductor has to be very robust and has to have maximum area exposure with the formation, okay. But the whole story here was to tell you that here you have your conductor, okay, someplace, and that's holding everything, okay. That's holding the so you have these wells, these satellite wells, okay, and then after that you have a central module that you call a manifold module, okay, and from here you put either what we call a jumper, okay, or simply a flow line. It can be a flow line if it's far away, or it can be a jumper, okay, if it's close. And a jumper is exactly what is showing in the figure here. Here we have a well, okay, and here we have this manifold module, okay, where we are going to take the production later, and we just put a rigid piece of pipe that is called this jumper that connects the two of them. That connects the well module, the Christmas tree, with the manifold. Okay. In that configuration, so that's a small, let's make it here so you don't get confused. That's a short detour to explain what a conductor is. And the drilling process. Okay. So if you look at satellite wells, okay, if we are looking, and I don't think that's what you're going to use here in Tanzania, okay, but satellite wells, they go to this manifold, okay, this manifold module that sometimes has to be big. So you have one flow line or a jumper that comes inside, okay. Remember what we were saying here, the top side, okay, the FPSO or platform, you have two separators, okay, the test and the production, okay. So to take the production from each well to each separator, what do you need? Just like in the land case, right? You need two lines. You need two flow lines. So you need to lay two subsea flow lines that go all the way here, okay. And then you have to put a header, right? That will be the header for production and the header for testing inside this manifold. And then what else do you need? The routing valves, right? The last part that we said. So inside here, why do we make it inside and not outside, not here? If we put the splitting point here, we are going to need two lines, right? And then it's more expensive. If we put the splitting point inside, then we need just one line from the well to the manifold. Okay, so here we put one valve here, and we make another valve like that, right? And here we do exactly the same. I'm going to make more room. But you see, it's exactly the same like a land-based manifold. Okay, where you have two headers, the test, let's put it here T, and let's call it here P, and you, inside the manifold, you decide where to send the well to. Okay, you can decide to send it to production or send it to test. Okay, that's the satellite configuration. Okay, where you have satellite, they drill, they are in its own module, and you send a line to that manifold module. Okay, or you can have also, let's write it up here, let's call it template wells. And in the template wells, the well is drilled in the same manifold of the template, in the same manifold template. Okay, so the way it looks like, it can have many different wells, but what Statoil Equinor likes is to have a 4-well template. Okay, you can have 8, you can have 12, you can have as many as you want, but Equinor, Statoil, they like 4. So we are going to show how the 4 one looks like. In that template, you have one central part, which is the part where you have the manifold. Okay, but everything is part of the same module. And then you have a hole here, a slot, where you can place the wells, okay? But all of this is part of the same structure. So your wells are here, okay? And you have here inside the manifold with the two headers. Okay, you have the two flow lines. Okay, and you have actually your valves here. One valve goes here, one goes here, and it's the same for all the wells. Okay, just I don't want to make this one messy. So let me show you how it looks like. Okay, it looks something like that. That's from Statoil, I think so, Equinor. Okay, so you have these 4, you see the slots, they have some covers on the slots. So when you are drilling, you put the structure on the seabed, and then you open the lid, and then you start and you perforate, you make your well there. Then you close the lid, open the other one, and perforate the next well, and so forth. Okay, and in the center, you see this part here, that's where you have the manifold. Okay, so this structure, you see, it has some supports. Okay, the well is not painted here, but this structure is just to hold the weight of the structure itself and just the weight of the manifold. The weight of the well is held by the conductor always. Okay, the well is never held by the subsea structure. Yeah, so maybe let me make some more space here. Yeah, I will put it just let me just copy that figure. Okay, that's how it looks like. They are about to deploy it on the seabed. And I want to show how the manifold looks like on the inside, okay? Just before we go back to our exercise. Okay, I'm going to paste that here. Okay, but that's the manifold, and the manifold, the way it looks like, you see here you have the lines coming from the well, okay? If you see here, that's where the well is connected. You have this strange shape, okay, that allows the well, if it stops production, it's going to shrink, okay? It's going to cool down. So it's going to reduce a little bit its position, okay? I think it can be from maybe 20 centimeters to half a meter, something like that. That it will change due to expansion. When it starts production, due to the heating, it will expand and it will grow, okay? It will go up. So that's why you have this shape to give some flexibility for that expansion and contraction. There you have these two valves. How do we call these valves? The routing valves, right? Okay, and then one of the lines you see you have one small here, one goes to the manifold, this manifold, or this one goes to the other manifold, and here you have your manifold. Okay, you have all other kind of things, don't pay attention, okay, that you will cover more in detail in the subsea course, but you have basically the line that comes from the well, then you have the two routing valves, and then you have one that goes to this manifold and one that goes to the other manifold, okay, just like what we discussed before. Now, there is one thing that we have in this field, okay, in this block 2, that is this distance. What is the distance between the well and the separator? It's very long, right? It's 80 kilometers. So it will be extremely expensive to place just two lines in parallel, all the way from the field, all the way to shore. Okay, it will be extremely expensive to make two lines. So the solution they made there is that they are not going to have two lines, they're going to have just one line. Okay, they're still going to use template. Okay, they're going to use a template well. Okay, but here they're going to have just one line. Okay, and they say that's at onshore, okay, and they say we are going to place we're going to place a multi-phase meter. Okay, we're going to place a meter inside that is going to be able to measure how much gas we are producing, okay, and we trust that meter. Okay, therefore you don't have to have a test separator, you can just have one line that goes all the way to shore. Okay, be aware that multi-phase meters are not very precise. Okay, you need to calibrate them very carefully, and if the conditions change of pressure and temperature or of liquid that you have, they have to be recalibrated again. Okay, and this meter is going to be 2 kilometers down in the seabed, 80 kilometers from Dar es Salaam. Okay, so it's going to be very tough to retrieve it, to calibrate and put it back in place. Okay, but they say we are okay with the accuracy. Okay, we are okay with the accuracy and we can live with that. Okay, if they were in Brazil, actually Statoil has a field in Brazil. Brazil doesn't accept this multi-phase meter at all. Okay, they say we don't trust multi-phase meter. We don't accept that you use multi-phase meter. You have to put two lines. Even if you're 80 kilometers from shore, 100 kilometers, 200 kilometers, you have to use two lines. And you have to use a test separator. Okay, that caused a big increase of cost for the project. Okay, here in Tanzania, they accept to use multi-phase meter. That's why you can use one line. Norway, they also accept. Brazil, maybe they are special, they don't accept. Okay? They say no, it's not enough. We need to have two lines. Okay, so now that that's clear, now we can open the exercise so that all of us wake up. Let's open the exercise I gave you today on the memory stick, okay? The one called Block 2 Offshore Tanzania. Okay, and go to the tab called Data. Actually, just go to the one that says Field Layout. Okay, and that's very simplified. We know that the distances are not exactly symmetric, that they are located in slightly different place, but at this point, that's the system we're going to work with, okay? The simplified system. Okay, so you see we're producing only from Safarani. You have, how do you call this guy? A well template, right? Well template 1, Safarani 1, well template Safarani 2, well template Lavani 1, and well template Lavani 2. Then after that we have a flow line that goes all the way to this PLET. PLET stands for pipeline entry terminal. Okay, and then from there you have a long pipeline, 85 kilometers to a separator, and here you have the LNG plant. So now you see a kind of an issue, right, compared to what we did before. I taught you yesterday and today how to make analysis on a single well, equilibrium. You're experts on that right now, right? You know how to take any well, any kind, you know how to make equilibrium. The problem here, now we have a system of wells, okay? We have actually, we have how many wells we have? 12, okay? 12 wells. So how to deal with this system? We only know how to deal with, one single well. I'm going to teach network maybe tomorrow, okay? This is what I call a network, okay? A subsea network. To be more specific, they call it gathering network, okay? Because the function is to gather, commingle the production of all wells and take it to the LNG plant. So the assumption we're going to make is we're going to say that, oh, well, we don't have, let's imagine that we are in an early phase in the field, okay? We don't have much information. They are still drilling some appraisal wells, okay? They're trying to get the size, they're trying to get that. So we're going to say all wells are identical, okay? Just to make one assumption. All wells are identical. And moreover, all the distances of all flow lines are identical. All flow lines are identical. Okay? And one more thing, we're going to say that all wells drain from the same reservoir. Is an approximation, okay? We're going to make our life easy now, at least like the first stage. We're going to say all wells drain from the same reservoir, from the same tank, although we know it's not correct. We have two, Lavani and Safarani. All the wells produce the same, the tubing length is the same, the IPR is the same. These flow lines, they are identical, okay? And then you have that. If you make that assumption, then we can say, okay, that this Q of the field, right, that this rate flowing through here, how much will it be? Q of the field divided by 4, right? And we can say that the rate of each well will be the Q of the field divided by 4 divided by 3. Yes? So it will be Q of the field divided by 12. If everything is identical, okay, that means that all wells will have the same PWF and the same PWH, right? Every well will have the same. So it doesn't matter which well I look, which well I analyze, all the wells will be exactly identical. So I suggest to make equilibrium, okay? So we're going to make equilibrium along this line, okay? Then along this flow line, and then along one of the wells. Just looking at this flow path, okay? And all the rest we are going to neglect. All of the others are exactly the same. Okay, but we are looking at the flow line. Be careful, here we have to use the rate of the whole field. Okay, then we go from here to here, we have the rate of the field divided by 4, and from here to here we have the rate of the template divided by 3. Okay, so let's do that first equilibrium. Okay, let's go to our Excel sheet to see what do we have. And we are going to make that for, let's say, initial time 0, okay? Here we are saying, the way I'm going to do it is the way accountants work, okay? They use, when they put a year number, it's going to be the end of the year, okay? So the field starts to produce in year 1, beginning of year 1, okay? But I'm saying here, the end of year 0 is actually the beginning of year 1, right? Okay? So that's how I'm going to make it. The Q of the field, make it a bit bigger, I think. Okay? The Q of the field, I have it up here, it's going to be 18 million. So I just take it up from here. Okay? It's going to be 18 millions. The Q of the well, well, first here you have Q of the template in column N, okay? So let's fill that first. Q of the template will be the Q of the field divided by 4, okay? 4 is in B17. B17, okay? And I block it to avoid problems. And finally, I can calculate the Q of the well, okay? That will be the Q of the template divided by the number of wells per template, which is 3. And I block it. Okay, so I just calculate using the same thing. I have the field, then I go calculate the rate of the template, and then I go and calculate the rate of the well. I'm getting that the rate of each well is 1.5 million. Okay, and I'm using just simply these two cells. Yes? That one will be the rate of density divided by the number of wells now the Q, is the rate of the divided by the the rate of the well will be the curve equal to the rate of the density. The density is frequency divided by okay, now we have all the rates we need, right? In all the elements we have. We have flow in the well, then we have flow in the flow line, and then finally we have flow in the pipeline. Okay, we have the three rates that are of interest. Now, what have we done in flow equilibrium? The first step is define a point of interest, right? At this point, we want to make it convenient in a place that is, is a clever place. So, you know already, right, from what we have done before, what will you have to do to keep plateau rate at the beginning? You have to choke, right? Okay, so where is the choke in this drawing? Is this valve here? Okay, so we're going to put a choke for every well that is going to bridge the difference in pressure. So I suggest we use that as, as the equilibrium point. So what we have to make is from the reservoir, go to the bottom hole, and then go to the wellhead pressure of the well. We stop. We calculate the available pressure at the wellhead. Okay? What is the next step in flow equilibrium? We go to the other boundary, right? The separator, and we move from separator to plate, and then we move from plate to template. And really, this point is very, very close to the exit of the choke. Okay? So we can say that's the pressure at the discharge of the choke. We compare. Okay? If this one is bigger than that, I have to choke. Yes? So let's do that. Let's move from reservoir, bottom hole, and then we move to wellhead. Okay? Let's do that step first. Okay, first we need reservoir pressure, right? Reservoir pressure is, we have it up here. We are making this calculation at initial time, okay? At time end of year 0. Let me block that, okay, that pressure. Then, how do I move from reservoir pressure to bottom hole? IPR, right? Inflow performance relationship. And let me see how we call that. I think that has the same name. Okay, if we go to flow equations, we go, you see here, IPR, that one gives you the rate. That's not the one I need. I need IPR PWF. Okay, that gives me the flowing bottom hole pressure. Okay, so so let's call that here. That will be function. I can just also type it, IPR PWF. I need the back pressure coefficient, which is back pressure coefficient is 1, 2, 3. I have to block it with a 4. Then the back pressure exponent, which is N. N means I wake you up in the middle of the night. And what does N mean? I have an N of 1. Darcy flow, yes. And then I have reservoir pressure is this PR. Okay, I don't block it. I want to drag it down such that it will take another pressure here. And the rate, what rate do I have through the formation towards the well? 1.5 million, right? Simply that. Okay, give me 374. That's the flowing bottom hole pressure. Yeah, is that pressure? Reservoir pressure? Is that? The rate of why are you getting? Ella es Winter. IPR reservoir pressure is line 23. Right. Column H. Don't block it. Don't block it. And then the rate is in column C, line 20. That's the rate. And you don't block it. Okay, so we have now reached the bottom of the well, okay? The available pressure at the bottom of the well. And that tells me that I have, it's like a 16 bar pressure drop. We call that drawdown, okay? Delta P in the formation. We have a 16 bar drawdown. Now we have to move from the bottom of the well, we have to move to the wellhead, okay? What equation do we use then? The tubing, right? Which pressure we want to calculate, P1 or P2? P2, right? We always say the flow is going from bottom hole to top. Bottom hole is 1, that's the one we have, and 2 is the one we want. That's the wellhead. Okay, so let's say here, I say tubing P2, okay? Tubing P2. And here I need the CT, the tubing constant, coefficient, and I block it with F4. The elevation factor, S, it's B10, and I also block it. P1, the inlet pressure to the tubing, that is PWF. Okay, I don't block it. And the rate is the same rate as the well, right? I'm still looking at the well. Okay, and that gave me that I have a pressure drop of 30 bar in the tubing. Okay, more or less 30.5, 31.5, 30.5. Okay, now we have moved from bottom hole, reservoir, bottom hole, and wellhead. We stop there. That's our equilibrium point. okay, before and after the choke. Now we have to move from the other boundary, separator, all the way to plate, okay, and then from plate to template. These are the two things we need, from separator to plate and plate to template. Now, so P separator, that remains constant always. So I'm going to use simply this number here, B14, and block it because it's going to be constant. How do I calculate the pressure at the plate? Counter current, and I have to use, you know, that flow line, actually, it has some inclination, okay? Because you saw the map, right? It has some inclination going up. There is 2,200 meters, more or less, and then it starts to go up all the way to shore, which is 0, okay? So it has a change of elevation. So in reality, we cannot use exactly horizontal flow line, but we have to use the equation for an inclined flow line or pipeline, okay? But we already discussed that we can use exactly the same tubing equation, right? But, you know, with the constant of the flow line and the elevation of the flow line, okay? So that's exactly what we have here. If you see of the pipeline, okay, we have pipeline elevation coefficient S and the pipeline coefficient, okay, pipeline coefficient. These two numbers, okay. So let's use the same tubing equation, okay, because it's this. I don't think we have a flow line, inclined flow line equation. Let's see. I don't think so. We have tubing, we have line, and this is horizontal line, okay? But our line is not horizontal, it's inclined. So let's use the same tubing equation. We have P2, right, the separator pressure. We want to calculate P1. So we want to use the equation tubing P1. Even though it's not a tubing, okay, it's a flow line. But we said it's the same equation. Tubing P1, and here I have to use the C of the flow line, of the pipeline, sorry, and I block it, S of the pipeline, and I block it, P2, P2 will be the separator pressure, okay, and then the rate, what rate should I use? I should use the rate of the field, right? That's the rate that is going through that pipeline, okay? The rate of the field. $75.1. That tells me that for the gas to go through a distance of 85 kilometers through that pipe, there is a pressure drop of 40 bar, okay, on that pipe, which is not much. Then you have to use tubing P2.
We're supposed to consider also we are we are using the Lewin equation, even though it's not a theory. It's a flow line, but it's an inclined flow line. Okay, we have moved from the separator to the plate. Okay, now we have to move from the plate all the way to the template. Okay, for that, this pipe is indeed horizontal. Okay, and which equation are we going to use? Line P1 or line P2? Let's see the direction, right? The flow goes in this direction. Okay, therefore, this is 1 and this is 2. 2 I have, and I want to calculate 1. Okay? Therefore, I need 9P1. Let's see where I have that on the Excel sheet. P template, okay? That template will be equal to line P1, okay? The pressure at the inlet of that line, and that depends on the pipeline flow line coefficient. Don't be confused, is this 11, okay? B11, I block it. P2 will be the plate, and the rate will be the rate of the template, which is in column N. Okay, it gives me 1.6 bar. Therefore, very little pressure drop between the plate and the template.
Okay, 1.7. What is the delta P of the choke? Wellhead pressure minus pressure at the template. Okay, 76.7. And this one will be the same as this one. Okay, wellhead pressure, available pressure minus required. Okay, we have successfully calculated but we were fixing the rate. Someone gave us the rate, but you have to verify if the delta P of the choke is positive. Okay, so you have to make the calculation anyhow, just to make sure this delta P is positive. Okay, it means that yes, you can produce the rate, and you will have to put a delta P at the choke of each well of 267. Okay, even though you say, well, it's trivial, you already fixed the rate, but I have to verify. It's not enough that I fix the rate. I have to verify that I can produce that rate. Now let's move to end of year 1. Okay, will be beginning of year 2. And here, so what's going to happen with time when I produce the rate? Okay, reservoir pressure is going to start to drop. Okay, and so far we haven't discussed how we are going to calculate that. Okay, so for that we are going to make first an assumption. Okay, so we say we want to calculate how to calculate P reservoir pressure as a function of time. Okay, that's the main purpose, what we want to calculate. So the assumption we are going to make, right, we are using steps of, okay, so far we calculated the rate here. We're going to assume that rate will remain constant, okay, from year 0 to year 1, which in plateau, it's okay, right? That's actually what happens, okay? But then when we enter into decline, okay, it's going to be an approximation, okay? Because when we enter in decline, actually the profile is going to look something like that, okay? Okay, therefore, the area under the curve is the red one. Okay, when we assume that the rate remains constant for the whole year, okay, or for the whole period, we are actually assuming that our area is the blue one. Okay, but let's say that that error is small. Okay, just for now, assuming that that error is very small. Okay, so how to calculate that? If we, maybe you're familiar, I think Golan, did he cover material balance? No? Okay. So it's something that we call dry gas material balance, okay? And the way we do it, I'm not going to derive that here just now, but I'm going to say, imagine we have a reservoir, right? It's a tank. And the tank has a fixed volume, BR, okay? And initially have some pressure 1, okay, or some reservoir pressure. You have a reservoir temperature, and you have some amount of fluid inside. Then I go to a second stage where I have exactly the same tank, exactly the same volume, but now I have taken out from the tank, okay, some amount of NP. Some amount I have produced out of the tank. And now I will have an N, okay, minus NP. That's the amount of fluid I have on my tank, and I want to find out what is now the pressure. That's initial reservoir pressure, and that's the pressure at that time. Okay, how much mass I have taken out and how much so if you look at the equation, right, the real gas equation, you have V R set T, okay, TR, that is constant, that is so this specific volume, what is the definition of a specific volume? Is the volume divided by the mass, right? Okay, so you can express the mass at initially can be equal to PR initial VR, okay, always has the same volume, divided by R set I initial TR. Okay, that's the amount of mass I have initially in the tank. Okay, initial reservoir pressure, the volume is always the same. We're assuming it's not changing much, although it's going to change because of rock compaction. Okay, when you reduce the pressure, the rock simply just becomes smaller. Okay, and the M at that location star, okay, the M at this condition star will be equal to P R times VR, the same volume, divided by R ZI TR. So sorry, ZR, not ZI. Okay? Then I'm not going to show the whole derivation, but I can express basically NP has a function of this MI minus M star. Okay? But I have to make a change because N is in standard conditions, okay? This is in standard conditions, and this guy is in mass, okay, in kilogram. So I have to make some conversion. But, let's leave it for time being, and the equation you obtain, okay, the final equation, but you know where it came from, more or less, okay? You apply the tank at initial condition, the tank at any generic condition, assuming you have drained part of the material from that tank, and then you make the difference, okay? And that's how you find NP. The final equation is PR is equal to is PI ZR ZR over ZI 1 minus NP over N, or sorry, GP, here we're saying is gas, right? It's not N. So it should be G. That we have to be careful. This is also G. Sorry for that. G, that's G minus GP. Okay, so if you substitute all the values, if you make the change between mass and volume, you find out that equation. Okay, which is the material balance assuming dry gas and neglecting compressibility, rock compressibility. Why? Because you're assuming that the tank, the volume of this tank, this volume R, is remaining always constant. In reality, when the pressure lowers, that's like a balloon, okay, that is going to maybe shrink a little bit, okay? You have some compaction happening. Now, what is that? I think we covered that yesterday, okay? What is GP over G? Okay, GP, how much I have produced from what was originally in place, G, okay? Therefore, that is what we call the recovery factor, okay? The recovery factor, how much I have recovered so far. So that equation, sometimes I put it like that, PI ZR over ZI 1 minus the recovery factor. And that equation is the equation, if you go back to the BBA, if you go to material balance, that's the equation you have programmed there. PR ZR PI over ZI 1 minus RF. Okay, that's the equation you have programmed. Now we have a challenge here, okay, that I haven't told you about. PI we have, right? Okay, let's look here. What do we have? We have this PI, right? We have the deviation factor for, if you remember, was that plot. Where is the, I think I have the plot. Maybe I have a nicer picture here. Okay, is this compressibility factor or this deviation factor? Okay, where I enter into reduce pressure. Okay, let's make it maybe smaller. Okay, so we have initial reservoir pressure and temperature. Therefore, we can find the initial set, right? This guy we have. The recovery factor, we can assume, right, that for next year, let's say at end of time zero, we found the rate, right, of the field. Now, year one, we're going to assume that we produce the Q of the field, okay, if we take a plot, okay, time versus Q, we're going to assume that rate remain constant until next year, until end of year one, okay? Therefore, we can calculate the NP, okay? NP will be the area under the curve. Okay, instead of making any integration, anything, we just say assume the rate remains constant throughout the year. Now, and that gives me this recovery factor. Okay, so this guy I have. So now, what is the problem between these two? You know that ZR, the deviation factor, is a function of reservoir temperature. I have no problem with that. But I need also reservoir pressure. And reservoir pressure is exactly what I need to calculate. If you see, it's like an implicit equation. This equation here, I need the pressure that I'm supposed to calculate. Okay, so I have a big problem. In reality, the way to solve it, okay, I'm just going to say here, the way to solve it, let's make a small, so I assume a PR, okay, then I calculate ZR with the chart, okay, and then I, from the equation, calculate PR, okay, and then I check, is PR assumed, okay, the one that I assume up here, equal to PR calculated? If yes, that's the solution. If not, I have to assume now another PR. And it's an iterative process, okay? I assume a P, I calculate Z, I use it in this equation, I calculate P, and then I verify. Are these two the same? No. I return and go back the... To make our life simple in this exercise, we're going to say the variation in pressure from year to year is going to go very, very slow, which you will see is correct, okay? It's going to go very, very slow. Therefore, it's a good approximation, okay? We have with time the reservoir pressure, and we have PR1, PR2, PR3, and so forth, okay? Time T1, T2, T3. So we are going to assume that PR is slow changing, okay? It's a slow changing. Therefore, I can say I can calculate ZR2 with PR1 and TR1, okay? With the conditions from the previous time. Because they're changing so slow, I would say I calculate the conditions of year ZRI with the conditions PRI minus 1 and TRI minus 1. Well, actually, reservoir pressure doesn't, the reservoir temperature doesn't change, okay? So that's, okay? Now, also, to avoid going into the graph, trying to read the number and spend time there, I have made a VBA function for that, okay, to read the deviation factor that contains a chart. And it's here, it's in C factor. If you go on the modules, it's called C factor standing, and you have to provide P and T, the specific density of the gas, and the units, okay? We're going to use in metric number 2, and we're going to take a break soon. Okay, so let's use that. Okay, so first, let's calculate initially how much I have produced. 0, right? No production. How much I produce in the year between 0 and 1? Delta GP, okay, I will say I will produce the rate of the field, right, times the difference in time in years between this year minus that year, okay, assuming the rate is constant from 0 to 1, okay? But remember, this unit, this one is in years, okay? And this one is in standard cubic meter per day. So I have to convert between, let's make it here very quickly, that annotation, okay? Delta GP is the rate of the year times 1 minus 0, okay, in our case, or year Ti minus Ti minus 1, okay? But this one is in years, and this one is standard cubic meters per day, okay? So they don't cancel out. We need something that gives you the number of days per year, which is, that we discussed yesterday, the uptime, yes? This is the uptime. So I have to multiply times the uptime to such that the units make sense, okay? So we have the rate has to be of the whole field, right? How much I have produced in total from the reservoir, times the difference in years, times the uptime. The uptime is someplace up here, okay, in B4. We block it, okay? So that means I have produced during year 1, okay, 6.5 billion. That's what I have produced. And now the GP in year 1, at the end of year 1, will be the GP from the year before plus how much was produced in the year. Okay? Okay, just don't be confused. This is how much I have produced from the reservoir total, and delta is how much I produced in that year. Okay, here is from 0 to 1, I produced 6.5. So this is how much I have produced total from year 0. Okay? Got the same number?
Okay, now let's calculate the deviation factor at the initial reservoir pressure. Okay, set I. Set I, so I call that function C factor standing. Okay, and that requires pressure, reservoir pressure. I don't block it. Okay, that requires reservoir pressure, requires reservoir temperature, which is up here 70. Okay, let me just make it like that so it will be better. Temperature, which is 70, that I have to block the specific gravity of the gas, which will be is someplace here 0.57, that I have to block as well. And then the unit, you remember which unit was it? We're working in metric, so we have to put 2. Again, I'm getting a deviation factor of 1.04, and that's how much it deviates from ideal gas. Okay, it's a correction number that tells you how much it deviates from ideal gas. And it can go from maybe 0.7 all the way to 2, 2.5, depending how off you are. What you need? Yeah, if you go to the VBA function, how it looks like, it tells you that you can give the input in field or metric. Yeah. So if you use in PSI or Fahrenheit, you will have to put 1 because it makes the conversion inside in the function. The recovery factor is how much I have produced from the field divided by the initial gas in place, which is in cell B3. Okay, so you see for the first year you have recovered only 2%. Okay, that you have. You remember I told you, right? Plateau, a rule of thumb is that for gas, I think we discussed that yesterday. Yes, we did, right? Rule of thumb was that
Where is it? I cannot find it. Yeah, here. Okay. For gas, the annual how much I take annually is 2 to 5% of the total recoverable reserves. Okay. In our case, we are taking 2%, but not of the total recoverable reserves, but of the initial gas in place. Okay. Which is going to be, so I'm taking more that that what according to the rule of thumb. Now to calculate pressure, I use the material balance equation. Okay, so I go here how to call it MB gas tank. Okay, so I call it MB gas tank PR. Okay, and here we take initial reservoir pressure. That will be this number here, and I block it, F4. Initial deviation factor is that number here, and I block it. Now, the deviation factor of that year, we said we are going to use the one from the previous. Okay? So the previous in this case is the same as the initial. Okay? But when I pull it down, it's going to take the one from the previous year. Okay? But for this particular year, for the end of year one, it's exactly the same. The ZI and ZR are the same. The recovery factor is this one. I don't block it. And then I find that the pressure dropped 8 bar in a year. Okay? Okay, so you should have reached up to that point. Okay, so first, just to summarize, we have done flow equilibrium. That's all of this part to the right, okay? And we found for beginning of the production, end of year 0, we found that, well, we need a choke of 267, but we can produce actually that rate that we need, okay, by contract, 18 million. Then the next step was to say, the production that I found before, this 18 million, is going to be constant from 0 to 1, okay, throughout the whole year 1. It's an approximation. We know that, how it's going to look like, my approximation, something like that, okay? So I'm overestimating production, but I say, well, we can live with that, okay? So I say initially, I haven't produced anything from the reservoir. I have to calculate how much was produced in the year, okay? And I suggest using that formula, the difference between the years, the number of days, and the rate. And then we found simply, how much has been produced during the first year, at the end of year 1. Then I calculate the recovery factor. Then with the recovery factor, initial reservoir pressure, initial deviation factor, I can calculate the current reservoir pressure. Here I have made an assumption that the C of this year is the C of the previous, the deviation factor, okay? When I drag it down, it's going to take the deviation factor from, not from the initial, but from the previous year, okay? So if we have done all of our things correct, right? We can just drag down here we select the whole row, all of these cells, and we drag down, and now it will perform automatically the equilibrium for okay? We have also to drag this one first, okay? We have to drag this one, and here something happened. Okay, here I should block this because I didn't block it. Okay, and then I drag it down. Okay, I'm still keeping the same rate. And then now I find that the delta P of the choke is 259, okay? Which makes sense. I have to open the choke with time. Did you get similar numbers? Okay, I just drag down this line, and then I fix an error I had here. So it should be 18. That number should be fixed. And then, I should have this thing. So now let's select the whole row, okay? And we drag it down. Here I have made 35 years. We want to see what happens in 35 years of the field. I drag that column down all the way to 35. Okay? Take it all the way to 35 years. Okay. You have to have the difference between the years, not the sum. There you have. No, you have a sum there. I'm seeing it. Come back for the last part. So that's the table I found, okay? Or that you also, many of you found. And let's see some interesting things here on that table. So you can do some quality control, okay, of the data. And first, just look, we are fixing the rate, okay? So look that the fill rate should be constant, the well rate should be constant, and the template rate should also be constant, okay? They depend on each other, okay? So if I change this, I fixed, okay? This number I'm taking from the top, okay? From this cell here, okay? So all of them are the same. Then the rate of the template will depend on that rate, okay, divided by the number of templates, and the rate of the well depends on the template. I have made it like that. You will see very soon why, okay? Other thing is that I'm producing in plateau mode, thus every year I should produce the same, okay, 6.5. Look at the recovery factor. The cumulative production should be always increasing, okay? And the recovery factor should always also be increasing. You see that by year 35, the recovery factor is 73%, which is very high, okay? That's usually the case for gas, that we manage to recover 73% of these 311 billion. Another thing you could check, reservoir pressure should go down, okay? Here goes from 300 to 200. But interesting, so that causes that bottom hole pressure and wellhead pressure also go down, okay? But interestingly, separator pressure is constant, therefore the plate pressure is constant, and therefore the template pressure is always constant, okay? And the choke, the delta P of the choke is going to reduce, going down with time. So if you go now to the same Excel sheet and you go to the plot, okay, pressure versus time, one thing that you have to make, right click on the axis, format, and then just now make it go all the way to 35, okay, because we are predicting 35 years. So just put here instead of 30, just put 35. Okay, right click on the axis and then you put 35. One more thing is that this series, if you see here, it was going only up to 53, I think. That's the number some of you have, 53 and 53 here. But in reality, our data doesn't go only to 53, but it goes all the way to 58. Okay, so you have to click on the series, okay, and everywhere where it says 53, just change it by 58, okay? You delete the 8 and put the 3, delete the 8 and put the 3, sorry, delete the 3 and put the 8. Okay, so it should be 58 and 58. It should be only in two places. Then you do the same for all the curves. Sorry. Okay, so you see wellhead pressure, sorry, reservoir pressure goes down with time, which makes sense. Okay, then you have that flowing bottom hole pressure also goes down, and that makes sense, right? Because you have QG CR PR squared minus PWF squared to the power of n, okay? That one is constant, the Q of the well. This one goes down, therefore this one also has to go down, okay? According to the equation, to keep the same difference. If this one is constant, this one goes down, this one also should go down. Now, also wellhead pressure goes down, okay? And that's where I stop. Then I have separator pressure, is always constant. The plant likes to be steady with time. Then I have plate, okay? Plate is very close to template. So they're one of them, this is blue and this is green, but they are almost one on top of each other, okay? But they are constant. Where is the delta P of the choke here? Is the difference between the wellhead pressure and the template pressure, okay? So if you see initially, I need a very big pressure drop across the choke, but then I have to open and open and open until I reach this point. What happens there at that point? That's the end of the plateau, okay? That's where the choke is fully open and the two pressures, they become the same. The wellhead pressure and the template pressure. This is plateau end. And if you see on your data, it will be exactly when that difference becomes zero, which happens in year 27. This field, block 2, can deliver a plateau of 27 years, no problem, okay? And then it will start to decline. That means if I have a contract with the Asian market for 20 years, more than enough, okay? I can produce more than enough. Now, what happens after year 27, okay? Year 28, 29. You see that the choke becomes negative, okay? That means that if I still want to produce the same rate, I have to add energy, okay? I have to put a compressor. But they're not planning to put any compressor on this field, okay? Therefore, we have to reduce the rate, right? How do we reduce the rate? We have to change the rate, right? Reduce it such that the choke will be zero. After that point, after the end of the plateau, simply the choke is fully open. There is no choke anymore, okay? So the two pressures have to be the same forcefully have to be the same. So you can do it manually. Let's try with 17 million. Okay, exactly in year 28. Okay, you see now I got minus 3. Says maybe try with 16.8 e to the 6. Okay, minus 1, 16.7. Okay, 16.7. So in year 28, the rate has to drop from 18 to 16.7. Okay, to so that I can flow that rate. Let's say now for year 29, let's try with 15 million. Okay, I have too much, I have to choke, so let's try with 15.6. Okay, maybe try with 15.5. Okay, 15.5. And so forth. Okay, I can do it like that manually, or I could use the solver. Okay, so let's try to use the solver. In the solver, I say solver drive the delta P of the choke. Okay, this delta P of the choke to 0 by changing the rate of the field on that year. Okay. Okay, 14.3, and then I have to go to the next year, and then I simply change here 54, 54, and then I solve. Okay, and this one I suggest we take a lower number, like 13 million. Okay, and then we repeat the same with the solver. Solver 55, 55, solve it. Okay, once more 56, 56. We have 2 more years to go. 57, 57. Okay, and lastly 58, year 58. Okay, so I have found, after the plateau ends, year 27, I have found how much the field will be producing after that time. Okay, I can do it manually, changing the rate of the field in every year, or you can use the solver, whatever you prefer. Okay, and I'm going to plot now the rate, okay, in the same chart. I'm going to plot now the rate. So let's add one more, that's Q of the field. Mhm. Yeah, just put 13. In all of those last years, just put 13 million. Yeah. Just put there, no, 13 million by manually. Yeah. Because it's just the number is too high. So you're getting a negative, under the square root, you're getting a negative number. Okay, so just put 13 and then drag it down, and you will get rid of that error. Okay, and now you can start to iterate to change it manually to, well, the last two maybe you have to change to 9 or something lower. Okay, now the last part of the class I want to show. So just to show you the plot, okay, you can make the plot. So that's the Q of the field is constant. You get 20. How much was it? 18 million. Okay, until you reach year 27, and then you start to decline. And at that point, when you have 10, they say we abandon the field. Okay, so the field life is 35 years. You see something also interesting. After that point, the wellhead pressure and the template pressure, they become the same. Okay, they merge and they become the same, which is exactly what happens if the choke is fully open, right? They're in the same place, very close to each other, therefore they shouldn't be that different. Okay, and it tells you when you are in plateau, you just have to calculate the delta P of the choke, and I'm happy, my life is simple. But after the plateau, you have actually to make a solving process. Okay, you have to assume and try to find the rate. Okay, which is the equivalent of finding the intersection. Okay, you have to operate exactly at the intersection, 0. Okay, now maybe that will be a homework for tomorrow, okay? That you have to work a bit today. What happens if we increase the rate? And that's something we have to do, right? I told you that increasing the plateau rate is increasing the cost, but also is increasing the revenue, okay? So what happens now is if instead of producing 18 million, I decide to produce 25. Can I do it with this Excel sheet? Okay, if I have done everything properly, right, which maybe not, if I should only change this number from 18 to 25, okay, now you see everything changed automatically, okay, now the well instead of producing 1.5 will produce 2, okay, and let's see where is the end of the plateau. The end of the plateau now is in year 16, okay, which is not good for the contract, okay, I want to produce for 20 years. But yeah, so here I have to do exactly the same to change the rate, right? To find the depletion. So that will be, which column will be 39, 39, and 39. Okay, and then I go once more, 40 and 40, and now I have to go a bunch of years because now there are more years in which I don't have plateau production. Okay, and then maybe I have to change that rate. I have to put it maybe in 13. E to the 6. Only 10 more to go. 10 points. Okay, and that's what I get now. The plateau is much higher, okay, but it's much shorter. Now it's on year 16 and then it starts to decline. Okay, that gives me a very quick recovery of revenue. Okay, the problem is I don't deliver my contract for 20 years and I enter in decline much sooner. Okay, so let me just copy that. And paste it in the notes. So let's see, for a higher plateau, of 25 million, then I get the following chart, okay? And that's something we have to do when developing a field. We have to try with different plateau rates and see, which one, how it behaves with the rate, plateau rate versus the usually, if you make a plot of Q plateau, the trend is if I increase the plateau rate, the duration of the plateau is going to go down, okay? If I use a higher plateau, it's going to decline. For now, we have just 2 points. This point for 25 million, that give you 16, and then this point, it gives us 27, okay? But if you want, you can make for different points. Okay, so I suggest you make the calculation for 18 and for 25, and you save it with a different name, okay, such that you save let's put here higher plateau, because we are going to use it tomorrow when we include that in the economy, okay, when we make the economic calculations. I will give you, maybe I will try to upload it today, the results, such that you can compare with your sheet, okay? I can send you the rates with time that I found. Okay. Okay, so let's make, I think we can, leave it until now, okay? And then we continue the next part tomorrow. So here we said about how the tubing size affect the equilibrium, okay? The tubing, the diameter, how do you define it? Different things that you have to consider. Then we talked about the flow line equation. We made equilibrium with the flow line. In most cases, we have a flow line. Okay, it's not only we have tubing and formation, we also have a flow line. Then we came and say we're going to use this flow equilibrium, and that was really the main part of this class. Okay, to show you how do you use flow equilibrium to calculate a field. Okay, the field rate. And for that we use block 2. We use actually 2 of them, Safaranian and Lavani. Okay, and I gave you some information how the field is going to look like. Okay, that's going to create a lot of work for you, for Tanzania. And then we talked about the subsea layout, okay, or the subsea architecture, how it looks like, what kind of configurations you have, why we don't put two lines, we just use one, okay, which is saving a lot of cost. And then we said we can simplify this problem because it's symmetric, all wells are identical, and I can look only at that that path. Okay, I don't have to look at anything else. Tomorrow we are going to look what happens when you have a network. How do I calculate a network? But for now we were just looking at that flow path, just the pipeline, one flow line and one well. Okay, but be careful, we were using the different rate for each section. For here we were using the well rate, here we were using the template rate, and here we were using the field rate. Okay, then material balance we need to calculate what happens with pressure with time. When we are producing, taking material out, the pressure is going down, and we made our calculation. Okay, we started the way we do equilibrium from the reservoir to the wellhead, from the separator to the wellhead or to the template, and then to move in time, we are assuming we have this assumption that whatever we calculate at the beginning of the year will remain constant throughout the year. Okay? We can improve it, but that's the approximation we are using. And we found that, which makes sense. Initially you have a very big choke, delta P of the choke, but then with time I have to open the choke, open and open and open, and this field enters in decline in year 27. Okay, and after that, something interesting, we have to use the solver, or we have to do it by hand, change the rate until that becomes zero. Okay, the pressure upstream the choke and downstream the choke are the same. Because the choke is fully open, we don't have choke anymore. Okay, and then I made it here very quickly. What happens when you use a higher plateau? If I didn't screw up my Excel sheet, if I just simply change that number, everything should change automatically. But of course, when it becomes negative, the choke, I have to change once more the rate by hand. Okay? And you see the plateau is higher, I recover more money early, but then the end is shorter. Okay, it's only for 16 years. Tomorrow we are going to talk about how do we use these values for something called NPV calculations. Okay, NPV calculations, NPV stands for net present value. Okay, it's a number that tells me how healthy economically the project is. Okay, it's a number that you assign, and if it's very positive, it means that it's a very profitable project. If it's close to zero or lower or negative, it tells you it's not very good. Okay, to calculate this number, we need a few things, but one of the things we need is the revenue. Okay, the revenue stream, and the revenue we usually say is we have to calculate by year. Okay, so by year we have our production, okay, delta GP, and then we have what is the revenue, okay, and we have a price of the gas. Okay, therefore we calculate in each year the delta GP, we multiply times the price of the gas, and then that's how we get our revenue, how much we're going to get every year. Okay, we do that for every year. That's what the other, if you go to the Excel sheet, that's what we're going to do here tomorrow. Okay, we're going to take the production, we're going to calculate the revenue, but then there are a few things there. We have to put the expenses, okay, how much we have spent to install the field. In this case of this field, we have the plant, the LNG plant, which is very expensive. Okay, this plant that I showed before, where is it? Went away here. This plant is very expensive, and then we need the subsea system. Okay, we need actually all the wells and all the manifolds. Where is it? Okay, we need this, the manifolds. We need to pay for the wells. We need to pay for many things. And finally, we have the operational expenditures, which are, for example, the maintenance. You have to pay the salaries of the people. You have to pay for insurance. You have to pay for some chemicals you have to inject. Okay? So we have to put all of that into the picture to calculate NPV. Okay? NPV, we have to include the revenue. Actually, should be the opposite. Okay? But then we have to include also the cost. Okay? And cost, we have the CAPEX, what we call CAPEX, capital expenditures. And we have to put also OPEX, which are operational expenditures. And after all of that, we're going to get one unique number, NPV, that I can take a decision based on that. Okay. Okay. Any question before we close? No? So I want for tomorrow, if you can work a bit today on that, if you can just compute these two cases, okay? And we are going to have two production profiles, okay? And that we're going to use for the economic calculation and compare both, okay? What happens if we use a higher plateau rate? How much that affects the NPV? Okay, if you want, I can try to upload. I won't upload the whole solution, but maybe just the rate, okay, of the field with time, such that you can compare QC your results. Okay, I will do it today, tomorrow, today when I arrive at the hotel. Okay, that's all for today. Thank you for coming. Session closed.